Welcome to CS350. This is Karthik Gopalan. Today we will discuss the topic of input-output subsystem, or how the data is moved into and out of a computer. So let's first look at the various layers involved in input-output. At the topmost level is the user applications, which issue the read and write I/O requests to the kernel subsystem through various system calls. Inside the kernel, there are various layers of software that handle an I/O request, such as the file subsystem or the network protocol stack. When the I/O requests reach the bottommost layer of the software, these are handed over to device drivers. Device drivers are responsible for communicating with individual I/O devices. Specifically, these device drivers communicate with pieces of device called device controllers. The device controllers understand the characteristics of the I/O device and know how to interact with the operating system. Finally, the device controllers talk to the physical devices. A single device controller may be responsible for one or more I/O devices. There are various categories of devices such as SCSI, PCI, TAPI, character devices, and so on. The CPU exchanges data with the I/O devices and main memory through the system bus. System bus is basically a data channel through which data is transferred between the CPU, main memory, and I/O devices. So every time the CPU wants to exchange data with an I/O device, it would place the address of the device on the system bus, followed by the data. So the specific protocol for communication over a system bus varies from one system bus to another. In older systems, there used to be only one system bus for communication between these three components. But newer computers distinguish between different types of I/O devices. Particularly for communication with main memory, which is a high bandwidth communication, CPU has a dedicated system bus. Similarly, for communication with high bandwidth I/O devices, there may be a high speed system bus. And for communication with low speed I/O devices, there may be low speed system buses. For example, in the Intel processors, there is North Bridge and South Bridge for communication with high speed and low speed I/O devices. The electronic components associated with any I/O device is called a device controller. A device controller acts as an interface between the operating system and the physical I/O media. So its purpose is to convert a serial bit stream into a block of bytes, or to format the data as necessary, perform any error corrections, perform any buffering, and so on. So there are various modes in which the processor can can perform I/O operations. One of the most primitive modes is called programmed I/O. Let's say that you want to print a file to a printer. So in this example, we are printing a string A, B, C, D, E, F, G, H to the printer. So one way of doing this printing operation is that the CPU may transfer 1 byte at a time to the I/O device. So essentially the CPU may have a tight for loop where it would send 1 byte at a time. It would wait till the printer is ready. Whenever the printer status is indicated as ready by the corresponding device controller, then the printer would send a single byte to the printer. Then it would go back and wait for the printer to become ready again. So the while loop, which actively polls the printer register, is a busy loop, which means that during this time the CPU is not doing anything else. It's wasting CPU cycles polling the printer whether it's ready or not. If the I/O device happens to be a really slow device which takes a long time to print, then essentially we are preventing the CPU from doing other useful work. Needless to say that this mode of I/O operation is rarely used in modern computer systems. An alternative to programmed I/O is called interrupt driven I/O. So before we understand interrupt-driven I/O, we need to understand what are interrupts. So an interrupt works by allowing the I/O device to signal the processor whenever it is ready to accept an I/O operation or whenever it has completed a previous I/O operation. So an interrupt-driven I/O would work as follows. The device driver would initiate the I/O operation by talking to the I/O controller. The I/O controller would then perform the I/O operation. Once the I/O operation is complete, then it would generate a signal or an interrupt that will be received by the processor. In between initiating the I/O and receiving the interrupt, the CPU would be busy doing other things, such as executing other processes. However, between every instruction, the CPU would check the interrupt status to see whether the I/O controller has delivered an interrupt. So finally, when interrupt is received, the CPU would stop whatever it's doing. It would jump into an interrupt routine or an interrupt handler, which would then process the interrupt. It would process the information received from the I/O controller. And then finally, once the interrupt handler completes, it would return from interrupt, and the CPU would resume whatever it was doing before the interrupt occurred. So the second picture shown here shows the same process except from the viewpoint of just receiving an interrupt. The operating system uses an interrupt vector table to determine which interrupt handler to invoke. The specific interrupt vector table is architecture dependent. There are some interrupts are non-maskable, meaning that the operating system cannot disable those interrupts, and other interrupts are maskable. So in this picture, we show an example of the interrupt vector table in the Pentium architecture. The interrupts 0 through 18 are reserved for processor-specific events, whereas interrupts 32 onwards are maskable interrupts that can be generated by I/O devices. So typically I/O devices, when the system boots up, the I/O devices claim one of the maskable interrupts. So the interrupt-driven I/O would work as follows. When the CPU is ready to issue an I/O operation, it would enable interrupts. It would check if the I/O device is ready to receive an I/O request. Then it would write the first piece of data into the I/O device. So we are continuing the previous example where we are trying to write a string of bytes to a printer. So after writing the first byte to the printer, the CPU would then call the scheduler, which would then schedule some other process to execute on the CPU. So note that the CPU is not actively polling the device register, it is doing some other useful work at this point. Figure B shows the pseudocode for the interrupt service routine. So whenever the device controller for the printer decides that it is ready to receive, it has completed writing a byte of data, then it would issue an interrupt to the processor. So at that point, the interrupt service handler would be called by the processor, which would then check if if all the bytes have been written. If not, then the interrupt handler would issue the next byte to the printer. So once all the bytes um, have been printed, then there's nothing more to print, and at that point the interrupt handler would simply return back to the scheduler. So in every iteration, every time the interrupt handler is called, besides deciding the next step, in this case printing to the printer, the interrupt handler also acknowledges the interrupt, basically telling the device controller that it successfully received the interrupt. So one of the key requirements of an interrupt handler is that the entire sequence of tasks must be completed very quickly. because the interrupt handler executes in the context of another process which was interrupted when the interrupt occurred. A third mode of performing I/O operations is called direct memory access, or DMA. In the case of DMA, we want to take the CPU completely out of the loop of transferring data. So in this example, CPU simply talks to the DMA controller and sets up the I/O operation. At this point, the DMA controller then talks to the I/O controller, in this case the disk controller, to set up the DMA request. The disk controller then performs the data transfer by directly accessing the main memory. So note that the CPU is not involved in the data transfer. The data is directly sent from the disk to the main memory or read from the main memory to the disk. Once the entire data transfer is complete, the disk controller would uh, coordinate with the DMA controller, which would then issue an interrupt when the DMA operation is done. So by doing this, we completely take the CPU out of the loop in transferring data bytes. This corresponding pseudocode is also pretty simple. All that the CPU does is it sets up the DMA controller with the I/O operation it wants, and then once the I/O operation is complete, it would receive an interrupt. In the interrupt handler, it will simply acknowledge the interrupt and return back to the process that was interrupted. There are various types of I/O devices. We have discussed these earlier when we talked about kernel modules. Basically, the three major classes of devices are character devices, block devices, and network devices. Character devices offer a byte stream abstraction. Examples include keyboard and mouse. Here there are no distinct message boundaries or block boundaries. Instead, the writer generates a stream of bytes and the reader reads a stream of bytes. Block devices divide up the data into, into equal sized blocks. So every read and write operation happens at a block granularity. For example, a hard disk might divide up data into blocks of 4 kilobytes, 8 kilobytes, or so on. So most storage devices fall in the category of block devices. Finally, there are network devices which offer the message abstraction, which is similar to the block abstraction, except that different messages can be of different sizes. So network cards, for example, are network devices where you can send and receive packets of various sizes. There are a number of other categories of I/O devices depending upon depending upon specific technologies. For example, USB, SCSI, FireWire, I2O, etc. Most of these categories of devices can be can emulate either character, block, or network devices. For example, you can have keyboards that follow the USB interface, or hard disks that attach to the USB interface, or network cards that attach to the USB interface. So now we will focus on two specific storage devices, hard disks and solid state devices. So let's first begin with hard disks. Hard disks, also known as mechanical disks, they organize data into tracks and sectors. So essentially hard disks store data as a persistent storage. Now, so disk has several platters, and data is in these platters is organized in tracks, and tracks are divided up into sectors. So each sector contains a unit of data that the disk head can read or write. In order to read a piece of data from a sector, the disk head would first seek to the corresponding track, and then the disk would rotate and until the corresponding sector is read by the disk head. So So there are, since this is a mechanical operation, there are various sources of overhead that we will discuss in a little while. But notice in this figure that there are two views of the disk. One which is the actual physical layout of the disk, and the second which is a virtual geometry of the disk which is exposed by the device controller. So in the physical layout of the disk, the tracks that are at the interior of the disk, they have fewer sectors, whereas tracks that are to the outside of the disk, they have more sectors. Thus the sector density varies as you go from inner tracks to outer tracks. However, it's very hard for operating systems to know like which specific make model um, has what type of sector and track density. So in order to simplify the job of device drivers, the disk controller may expose the virtual geometry which is shown in figure B. In the virtual geometry, you have the same sectors and tracks except that every track has equal number of sectors. So the simplified view is mapped by the disk controller into the actual physical layout. The mapping from virtual to physical geometry is performed by the disk controller. The operating system doesn't need to know the virtual to physical mapping. This basically simplifies the way that device drivers view the physical device. There are various factors that affect the read and write latency to hard disks. The most prominent one is the seek time, or the time it takes for a disk head to move from one track to another. On the average, seek time varies from about 5 to 10 milliseconds, sometimes even as high as 15 milliseconds. Rotational delay is the second mechanical component of read-write latency. Here, this is the time it takes for the corresponding sector which is being read or written to arrive under the disk head. Now, since the disk is constantly spinning, then on the average you may assume that it takes about half a rotation of a disk for the corresponding sector to arrive. So let's say the disk rotates at 15,000 rotations per minute. So this would translate to about 2 milliseconds of average rotational latency for every I/O operation. Finally, the actual data transfer time is the amount of time it takes to transfer a sector worth of data from the disk to the disk controller or to the main memory. This transfer happens at a very high rate, so it's usually in the order of microseconds or even less. Of all the three sources of latency, the seek time is the most dominant because there is a mechanical movement of the disk head across tracks. And for most practical purposes, the rotational latency and transfer time are ignored when computing the read-write latency. So since seek time is the most prominent component, various algorithms try to optimize the disk head movement to, uh, to reduce the seek time. So there are various algorithms for scheduling the disk head across tracks. So in this example, we have tracks numbered 0, 1, 2, 3, and so on. And the sectors marked with X represent the tracks uh, where there are I/O requests to be serviced. So the first algorithm called shortest seek first would move the disk head to the track that has the nearest I/O request. So for example, from I/O request number from position 11, the next closer request is position 12, and then at position 9 and so forth. So the disk head is acts in a greedy fashion by servicing the request that is closest to the current disk head position. Now obviously this gives a very high throughput because you service the request that is closest to the disk head. In this way you reduce the seek latency. However, it may so happen that some requests may be starved. For example, some requests may not be serviced for a really long time. Or so, for example, request at block 35 4 and 36 may have arrived a long time ago, but it takes a long time for the disk head to service those requests. An alternative which is more fair and yet provides a reasonable I/O throughput, this is known as the scan algorithm. In the scan algorithm, the disk head moves from one end of the disk to another and then back, servicing all the requests along the way. This is much like how an elevator services people moving up and down the floors. So, so in this example, the disk head would first move all the way to the right, servicing the request, and once it reaches the end, it would move back all the way to the left, servicing requests along the way. So this guarantees there will be no starvation, whereas it sacrifices a little bit of throughput in order to achieve this guarantee. The disk I/O throughput, the measurement of disk I/O throughput is not as simple as just measuring bytes per second. In particular, the seek time of in the hard disk affects the throughput measurement. If you're simply performing sequential I/O, it is reading, like say, block 1, block 2, block 3, and so on, or writing block 1, 2, 3, and so on, then there is very little seek involved, and as a result, sequential I/O throughput can be very high. On the other hand, if the I/O blocks being read have random positions, which we call random I/O, then the disk head may have to perform quite a bit of seek, and consequently the seek latency would play a major factor in reducing the I/O throughput. A popular way of measuring disk I/O throughput is called I/O operations per second, or IOPS. Since the data transfer time itself is very small and seek latency dominates, so people simplify the measurement of I/O throughput by simply measuring the number of I/O requests that are completed every second. It doesn't matter whether the I/O request is for a few bytes or many thousands of bytes. Each I/O request is, whether big or small, it's treated equally. So for hard disks where seek latency is a dominant factor, I/O operations per second is uh, a reasonable metric to consider. There is an additional component of the disk that plays an important role in disk I/O performance. This is known as the disk buffer. Disk buffer is a small amount of memory, basically random access memory, that is uh, that is integrated with the disk controller. So this is usually typically about 8 megabytes to 128 megabytes. The more memory you add to the disk controller, the more expensive the disk becomes. The purpose of the disk buffer is to hold data temporarily as the data is read or written to the disk. There are two ways that the disk buffer is used. One is as a read ahead data store. So whenever the operating system requests, say, block X from the disk, then the disk head may also read block X plus 1, 2, 3, and so on. Maybe it would read ahead these blocks, even though the operating system hasn't yet asked for them. So these blocks would be stored in the disk buffer with the hope that the next time operating system requests these blocks, they can be serviced without moving the disk head all the way back to the actual block location. So, so read ahead is acts a little bit like caching, except that you you expect certain spatial locality and accesses by the operating system. The second way that the disk buffer is used is for write acceleration. What this means is that whenever the operating system writes a piece of data to the disk controller would store this data in the disk buffer and immediately uh, interrupt the processor, acknowledging the operating system that the data has been received. So the operating system doesn't have to wait till the data is actually committed to the physical media. The operating system can proceed with other things. So you would notice that most hard disks have very low write latency, primarily because the data is simply written to the disk buffer and the operating system can then proceed forward. The data is committed from the disk buffer to the physical media at a later time. What this means is that if there is a power outage between the time that the disk is committed, the data is committed from the disk buffer, then the data could be lost. So there is usually some uncommitted data in the disk buffer, and if this is lost, then it could lead to disk corruption. Usually, on higher end disks, there's usually a battery backed uh, storage, which is used as disk buffer. So that way, if power is lost, then the battery backup allows you to commit the data to the physical media. The newer type of storage devices use solid state devices or solid state memory. So solid state memory is an alternative to the traditional hard disk or magnetic media. So these type of devices use NAND based flash memory to store persistent data. So in addition to the actual uh, persistent memory, there is a controller that performs a lot of operations much like a hard disk controller. For example, it may do error correction. There's something specific to SSD devices called wear leveling, and then stuff like caching, very similar to what we do with disk controllers. So there are no mechanical components, unlike hard disks. So there is no seek or rotational latency involved. There are various types of interfaces with which SSD based devices work, such as SATA, SAS, PCI, USB, and so on. And SSD devices can also be packaged in various form factors, from regular hard disks to thumb drives to embedded devices such as cameras, phones, and so on. SSD devices can also be used as buffers in hard disk. The disk buffers that we just discussed, you can replace the random access memory in those buffers with SSDs to improve the reliability in the event of power outages. In addition, if you have a SSD based hard drive, SSD based drive, then you could the drive itself may use DRAM as a buffer cache to increase to improve IO latencies. So so SSD is very flexible in various type of situations. How do SSDs compare to traditional hard drives? First of all, they have much lower random access latencies. So for example, access latencies of 0.1 millisecond are very common. At the same time, they also offer higher throughput than hard disks simply because there are no mechanical movements. There is also, in terms of reliability, the story is a little complicated. First, there are no moving parts, which means that the probability of a mechanical failure is low. On the other hand, NAND-based flash memory has a unique weakness that if you write to the same data cell more than once, if you repeatedly write to the same data cell again and again, then the reliability of that cell goes down. So over time, your writes will fail. So as a result, SSD-based devices, the device controllers have algorithms to perform wear leveling. What that means is that if you write a block of data again, it would actually be written to a different cell, so that all the cells were at the same rate. There's pretty much a fixed number of times that you can write to each cell. So in order to extend the lifetime of a solid state drive, the disk controller may perform wear leveling. Compared to hard disk drives, SSDs operate silently. There are no mechanical parts. They also have low power consumption. However, on the flip side, they have smaller capacities, and they tend to be more expensive than hard disks. So over the years, even hard disk technology has improved, and the capacities have improved dramatically. So SSDs are still catching up in that respect. There is one more type of storage access that is popular in network settings. In this type of storage access, you have a networked storage server. That is a server that sits on the network and has access to storage media, and the storage server is accessed by different clients over the network. This is commonly used in small organizations. For example, in our department, you commonly access your storage over the network from some storage server. This type of storage configuration is known as network attached storage, where clients do not use their local storage, but rather they rely on a networked storage server. Another configuration in large enterprise settings is called storage area network. Here you have a dedicated network called a SAN, which interconnects different storage devices. So you might have a RAID array, or you might have tape drives, or you might have more complicated storage configurations. They are all connected to a single dedicated storage area network. This storage area network usually has very high speed interconnect to enable large amounts of data transfer. Normally, application servers or servers that provide certain important services, they would be connected to the storage area network on one side, and they would be connected to a local area network or a LAN on the other side. So, so normal clients would communicate with application servers, and application servers would then communicate with storage devices on the back end through the SAN. So one property of SAN is that it provides virtualized storage. So it basically pulls together all these different storage devices and makes them appear as one or more block devices that are spread out over these multiple storage devices. So so this eases the administration complexity for system administrators. They view the entire storage pool as one virtualized storage pool rather than individual storage devices.